So here we're looking at the population of a city is P at time t years from a certain date. The population increases at a rate that is proportional to the square root of the population at that time. Construct and solve the appropriate differential equation and sketch a population time graph. So there's actually two things we have to do here. We have to construct a differential equation and we have to sketch. So looking at this, we've got two variables. We've got P and we've got T. Okay, and they're the two variables to extract out of this situation. Now we're looking at the population increasing, which means that P, our population, is always going to be greater than 0. And also because we're looking at time, time will be bigger than 0 too, because we're going forward in time. And we're looking at the increase that is a rate. So the first thing would be we're looking at the change in population with respect to a change in time. It's proportional to the square root of the population at that time. And we know that P would be bigger than 0. So remember, we can replace the proportional sign with an equal sign and then a constant. And because we know here that this is going to be positive and we're increasing, K will be a positive constant because we're increasing the population. Okay. Now this is a differential equation we're going to solve, so now we have to solve the dE. And I'm going to do this by separating and integrating. So I'm going to take the dt up to the right side. So we've got dp equals k root p dt. And I'm going to take the root p over to the other side underneath, just dividing underneath. I'm now going to integrate both sides. And I'm just going to rewrite this, instead of being square root p underneath as a denominator, I'm going to write that as p to the negative a half, and I'll integrate that side. It's got the dp there, so it's ready to go. And I'll integrate this side with respect to t. Now I'll point out this is a little bit, or done a little bit differently to the textbook, because in the textbook they actually move the k underneath with the p. I prefer not to do that because when you start moving constants, you'll end up with fractions, and then it just makes some of your algebra a bit fiddly. So I generally just leave the constants on the right side of the equation and move anything else that I need to move. So that's why I'm going to leave the k here. So I'm integrating the left side now. So we add 1 to the power, which becomes a half, divide by the new power. K is a constant and becomes the coefficient of t plus some other constant, we'll call it c. The half flips over and becomes 2 square root p equals kt plus c. And now what we're doing here is trying to get p as our subject, because we want to solve for always the variables on the top of the rate. So we're going to solve for p. So, oops, we've got, I'm just going to divide both sides there by by 2. So kt on 2 plus, I'll just relabel this, I'll call this a. I'll let a equal c over 2. So it's a bit nicer looking. And then p equals, this is a square root, which means that I can actually square this whole side here, like that. Alright, so that's the first part done. The next part that we're going to do is have a look at sketching this. So we've constructed the differential equation. So looking back at the question, we've done the construction, that's here. We've also solved that constructed differential equation here. And now what we're going to do is sketch the population graph for that. So I'm going to expand this out because it's a little bit difficult to see the way it is. I've got kt on 2 plus a, and it's squared. So I've got k squared t squared on 4 plus 2 kta on 2. So that one and that one. And then here we've got an a squared. So we've got k squared on 4 t squared, 2's cancel, plus k a t plus a squared, like that. So you can see that the graph we're going to be looking at actually is a parabola, and you can see that from here as well. So now let's sketch that. I've just expanded it so I can see a little bit more easily what's going on. I'm just going to bring that all over here and we'll do some sketching with it. Alright, at this point you can see for p equals, in the factorised form, when t equals 0, you can see here that p equals a squared, because these terms all cancel out. Okay, so what I'm going to do is I'm just going to draw some axes. Now we know we only need to consider the first quadrant because we're looking at t and p. It is a parabola, so that kind of shape, and you can see here that we've got a intercept on p of a squared. So it'll be that kind of shape there. Okay, you might want to give another point, maybe when t equals 1, you've got p equals k over 2 plus a all squared. So maybe point there 1, and then k on 2 plus a all squared. So what you're doing is you're really just showing the behaviour for this particular situation, and you can see the behaviour is that the population is increasing very quickly. So most population growth models tend to be exponential. This one's parabolic, but they all share the same kind of shape. So starting off kind of a bit slowly and then increasing very quickly. So that's the idea of solving a differential equation and then graphing the solution. I'd also encourage you to have a look in the textbook at the way it's been solved in there. It's been solved slightly differently to the way that I've done it. And the constant here that they find is a little bit different, but it's simply a matter of relabeling constants that's got me this a squared here. So as long as you keep track of what your constants are, so a equals c over 2, it will work out fine. So you might prefer to keep that as a c over 2 and then express it here, but there's no reason to, as long as you've stated. As you change constants, make sure you state what they are.